You don't hear it at first. You feel it. A low, invisible force building beneath your feet, rising through steel, through concrete, until the entire building begins to hum like something alive. Above you, hidden inside a casing the size of a house, a machine is spinning at 3,000 revolutions per minute. And if it fails, you won't see it coming. Because when these machines break, they don't slow down. They explode. This is the story of the steam turbine giants, the machines that powered the modern world, and the quiet forces inside them that could tear everything apart. Step inside one of these early power stations, and it doesn't feel like a factory. It feels like a cathedral. The ceilings stretch 3 stories high, steel beams disappear into shadow. The air is hot, thick with the smell of oil and steam. Every surface hums with energy. And at the center of it all sits the turbine. A rotor longer than a city bus, weighing as much as a freight car, encased in steel, spinning so fast your eyes couldn't track it even if it were exposed. It doesn't clank or pound like older machines. It roars, but smoothly. A continuous, relentless surge of motion. Superheated steam enters at extreme pressure, rushing through rows of finely shaped blades, transferring energy in a perfectly controlled cascade. You could stand just meters away and never fully grasp the violence contained inside. Because what made these machines powerful also made them dangerous. All that energy compressed into rotation, and once it's spinning, it doesn't forgive mistakes. By the late 1800s, the world had a problem. Cities were growing faster than anyone expected. Electric lights were spreading block by block. Streetcars needed constant power. Factories demanded machines that could run all day without stopping. Demand wasn't just increasing, it was accelerating. The old solution, reciprocating steam engines, had limits. They worked by driving pistons back and forth, and at small scales that was fine. But as power stations grew larger, that back and forth motion became a liability. More friction, more wear, more violent shaking. The bigger they got, the more unstable they became. And then someone asked a different question. What if steam didn't need to punch at all? What if it could just spin? That idea came from a man named Charles Parsons, and at first, almost no one believed him, because abandoning pistons meant abandoning everything the industry understood about power. It sounded risky, unproven, even impractical. But Parsons didn't argue. He demonstrated. In 1897, he brought a strange vessel to a naval event, a narrow experimental boat powered not by pistons, but by a turbine. Its name was Turbinia, and when it launched, everything changed. While the fastest ships nearby struggled to reach 27 knots, Turbinia surged past them at 34. It didn't just outperform them, it humiliated them. And suddenly, the impossible idea became inevitable. But here's the problem. Making steam spin a shaft wasn't simple. Steam changes as it moves, pressure drops, temperature shifts. Expansion behaves differently at every stage. Inside a turbine, those changes happen continuously and at extreme speed. Parsons relied on massive data sets, steam tables built from years of experimental physics to predict exactly how that energy would behave. Because guessing wasn't just inefficient, it was deadly. A miscalculation could cause imbalance, vibration, stress fractures, and at high speed, even a small flaw could become catastrophic. But once turbines proved they worked, industry didn't slow down, it accelerated. Factories replaced piston engines almost overnight, power stations scaled up rapidly, and engineers began asking the most dangerous question of all. How far can we push it? Turbines grew larger, faster, more powerful, and with every increase in speed, the margin for error shrank. A machine spinning at 1800 RPM was already dangerous. At 3000 RPM, it became something else entirely. Because at that speed, the rotor doesn't just spin, it stores energy, enormous amounts of it. Energy that wants to stay in motion. Energy that resists interruption. Energy that, if released, has nowhere to go but outward. Operators had to adapt. Old engines gave clear warning signs, loud knocks, visible motion, obvious failure points. Turbines were different. They were smooth, quiet, deceptively calm. Instead of reacting to obvious problems, workers had to detect subtle changes. A slight vibration, a faint temperature increase in a bearing, a sound that didn't quite belong. And this is where everything started to go wrong, because subtle warnings are easy to miss, especially in a room already filled with noise, heat, and constant motion. The machine didn't announce its danger, it hid it. Inside these massive halls, everything looked controlled, organized, impressive, almost beautiful. In fact, some people described power stations as architectural masterpieces, cathedrals of industry. But cathedrals aren't designed for violence. These buildings were. And the violence was always there, just waiting. If you enjoy these deep dives into real engineering stories, consider subscribing. It helps me keep making videos like this. Because what happened next didn't stay on land. As turbines proved themselves in power stations, engineers brought them into an even more unforgiving environment: the ocean. Inside a ship, there's no distance between you and the machinery, no open space, no safe boundary. Everything is compressed into steel compartments and narrow passageways. In 1905, one of the first ships powered entirely by steam turbines set sail, and it changed everything. Turbines made ships faster, more efficient, more compact. They eliminated the need for massive piston systems that took up valuable space. But they introduced something new: constant vibration. Not always dangerous, but always present. A deep, steady tremor that traveled through the hull, through the decks, through the walls. Passengers felt it in their beds, crew felt it in their bones. The ship itself became the indicator, and if that vibration changed, even slightly, everyone noticed. Because out at sea, there was no escaping it. No stepping outside, no safe distance. Just you and the machine beneath your feet. And as demand for speed increased, so did the pressure. Shipbuilders competed for faster crossings, governments wanted stronger fleets, companies needed tighter schedules. More speed meant more profit, more power meant more prestige, and turbines delivered. Ships began producing tens of thousands of horsepower, then hundreds of thousands. Each increase meant more energy, packed into spinning steel. But here's what made it dangerous. The increase in power wasn't always matched by an increase in understanding. And sometimes, the danger didn't come from failure. It came from routine. Overspeed testing was supposed to be safe, controlled, predictable. You intentionally pushed the turbine beyond its normal operating speed, just to confirm the safety system would shut it down in time.
It was like walking to the edge of a cliff, trusting the guardrail would hold. But what if the guardrail wasn't where you thought it was? In one case, operators worked with conflicting data. Different documents listed different safe speeds, different expectations. And in a machine spinning thousands of times per minute, uncertainty is lethal. Because hesitation is time, and time is exactly what the machine doesn't give you. It keeps accelerating. It keeps storing energy. It keeps moving toward a limit no one fully agrees on. And when failure comes, it doesn't come all at once. It builds, quietly. A worn component, a hidden crack, a slight imbalance, each one insignificant on its own, but together they form a chain. And when that chain breaks, it doesn't snap gently, it shatters. One of the most terrifying aspects of these systems wasn't the rotating steel, it was the steam itself. Because steam doesn't need moving parts to be deadly, it only needs an exit. Water expands dramatically when it turns to steam. A single cup becomes over 1,000 cups of vapor. Now imagine that expansion happening instantly inside a confined space. A rupture doesn't just release pressure, it erases the room. Visibility disappears, sound becomes overwhelming, and the same force that burns you also blinds you. You can't see, you can't hear, you can't escape, and by the time you realize what's happening, it's already too late. But even that wasn't the worst-case scenario. Because when turbines fail, they don't leak, they don't stall, they disintegrate. In 1974, at a major power plant, a turbine rotor failed during startup. It had been running for decades, maintained, inspected, trusted. But inside the steel, something had been growing, a microscopic defect left over from the original manufacturing process. Over years of operation, stress built around it, slowly, silently, until one day, under the right conditions, the rotor didn't bend, it didn't crack, it exploded, breaking into dozens of massive fragments, each one launched outward with tremendous force. This wasn't just a machine failing, it was stored energy being released all at once. And the most unsettling part? No one saw it coming.
Because the warning signs, if they existed, were buried deep inside the metal itself. Invisible, undetectable. That's the truth about these machines. They can run perfectly for decades and still be one moment away from destruction. And yet, people kept working around them every day because someone had to. Operators knew the risks. They understood the responsibility. Entire cities depended on these machines. Lights, transportation, industry, all of it powered by something spinning just meters away. There was pride in that, but also respect. Because turbines taught a hard lesson. Speed is power, but power without understanding is danger. Over time, the industry changed. Better materials, better inspection methods, clearer safety standards, designs that accounted for failure instead of assuming it wouldn't happen. But the machines themselves, they never became harmless. They just became better managed. Because no matter how advanced the technology becomes, the core truth doesn't change. Inside every turbine, there is a force that wants to keep moving, a force that cannot stop instantly, a force that, if released, will tear through anything in its path. And the only thing standing between control and catastrophe is the assumption that everything is still working, until it isn't. And by then, it's already happening.